In this video, we're going to talk about conjugate action, specifically for mechanical spur gears. Conjugate action, as applied to mechanical gears, assures that we have a constant speed ratio. This is something we discussed and introduced last time as an important requirement for mechanical gears. We're going to go through spur gear tooth force analysis as a means to understand how do we actually produce a gear set that provides conjugate action. We're going to go through a derivation of these constant speed ratio requirements for conjugate action. We're going to have a look at how we can actually generate, how we can construct the geometry of a gear tooth that's capable of producing conjugate action. And the term that we use to describe this geometry is involute. So we're going to look at methods for generating involute tooth shapes. Next, we're going through a physical illustration of involute shape generation, and I hope that this provides a lot more intuitive insight into how this particular gear shape works in providing conjugate action. We're going to talk about gear mesh requirements and something called contact ratio. Then we're going to cover a spur gear design procedure. This is a procedure-based design method that allows us to systematically go through the process of gear design and aids in managing gear parameter coupling. More specifically, we have relationships between different design variables and other quantities that describe the properties of these gear sets. And it's a challenge sometimes to manage all of these simultaneously. And so there is a 5-step procedure in the textbook that helps walk you through this process. Let's talk first about conjugate action. For mechanical spur gears, we're going to address how we can design the geometry of a gear such that we have a constant speed ratio. And it's a fundamental requirement for designing actual practical mechanical gears. This is one of the more challenging concepts that we cover in class. The mathematics isn't overly difficult, but the concept of why this actually works is one of the more challenging concepts in my experience. There is a web of interrelationships between things like design requirements and design decisions. We have these multi-stage links or different types of coupling between these quantities of interest, and so it can be a challenge to design mechanical gears. We're going to go through some simplified kinematic models first, and these are things that you have seen previously where you treat gears as rolling cylinders in contact. And in that case, we really can treat the gears as if they have a constant pitch radius. And here we make the assumption that there's zero slipping at this interface between the gears or the cylinders that are models of the gears. But the actual forces that would be present are quite different from the forces that are present if we have two gears in mesh with each other. Suppose we have these two rolling cylinders. They're each rolling about their own axis. They're in contact. We're assuming that there's friction between them and that there's no slipping between them. So if we rotate one, say this small gear, the input, if we rotate that clockwise, then the output, that's going to rotate counterclockwise at a lower rotational velocity. Here's a point of contact, and we can use that in measuring what the pitch radii are and calculating the speed ratio. A key difference here between this model and what happens with an actual mechanical gear is that in this case, the contact force is tangential to the contact surfaces. So we have this circular surface. As it approaches this contact point, we can think through, well, what direction are the forces going to be acting? If we're going to have a torque about this point, the center of the input gear, and if it's rotating clockwise, we're going to have a downward force that's acting at the point of contact, and that downward force is going to be tangential to the surface of the input gear on the left-hand side. And then the reaction force that's coming from the right-hand gear, the output gear, that's also going to be directed vertically, in this case upward, and it's going to go through the point of contact. And so again, that is a tangential force. But when we are looking at an actual set of gears that are meshed together and the teeth are contacting, the forces are very different. They're transmitted through compressive tooth contact, not friction. So, for example, here's a zoomed out image from the textbook. If we have an input gear on the left and an output gear on the right, instead of having just a single point of contact that never moves in between them, we have sometimes multiple gear teeth that are in, or pairs of gear teeth that are in contact with each other at any given time. And so we have these points of contact, and if the force is perpendicular to these surfaces as opposed to tangential, and that's the case here if we assume that there's no friction between the gear teeth, then we're going to have these forces pointing in some other direction. In general, they're not necessarily going to be pointing straight up and down in this view. In particular, the contact force when we have gear teeth next to each other, contacting each other, these forces we assume are perpendicular to the contact surfaces. And this is true if we have no friction. For conjugate action to hold true, we need to have a constant speed ratio. Earlier, we defined what speed ratio is. That's the input speed divided by the output speed. Also, we can calculate that as the output gear radius divided by the input gear radius. And often in the textbook and other places, you may hear a slightly different terminology regarding input or output gear. Sometimes the input gear is simply referred to as the pinion, and the output gear is more simply referred to as the gear. A requirement for practical gear design is to have a constant speed ratio. It's essential that this speed ratio does not vary with angular position. The position of the gear as it rotates through its various positions, and a way of quantifying that is saying that the derivative of the speed ratio with respect to the angular position of a gear must be 0. We're going to go through how we can actually ensure this is the case for a gear set by discovering a geometry for gear teeth that ensures this is the case. If we don't have this constant speed ratio, it can cause a number of problems. This is really important for us to have smooth torque output and precise motion control. So suppose we have this gear set with the input gear, gear 1, output gear, gear 2, and suppose we have a constant input speed that's provided to the input gear. Even if this is held perfectly constant, if we don't have a gear geometry that ensures conjugate action, we could have some variation in the output speed. And this is definitely not what we want. This can cause significant mechanical problems. Here's a nice animation that helps us to understand many different elements of what we're talking about in this lecture. So as we're looking at these two gears, we're zoomed in at the mesh interface, and here we can see as a pair of gear teeth come into contact, these arrows appear, and these arrows, they represent the force, the contact force that's perpendicular to the surface at the point of contact. And in this video and other places, I will refer to the point of contact C, and that's different from the pitch point in general. Now remember, the pitch point is a point where if we draw a straight line between the axes of rotation of each of the gears, it's going to be the distance R1 from the center of gear 1 and R2 from the center of gear 2, where R1 and R2 are the pitch radii for the respective gears. If we have the right-hand gear being the driven gear and the left-hand gear being the input gear, just referring to the geometry of the driven gear here, as the point comes into contact, the contact point is pretty close to the top land, the upper land of the tooth from the right-hand gear. But as we move farther down into the contact point is very close to the bottom land. So this contact point moves along the surface of the gear tooth as we change angular position. And if this point of contact moves, how is that going to affect the mechanical advantage and the speed ratio? Now, remember, this is how we derived the speed ratio earlier using this simplified rolling cylinder model. It's equal to the input speed over the output speed, or R2 over R1, or R out over R in, or torque out over torque in. So we can look at a velocity perspective, or we can look at a torque or force perspective in understanding what the speed ratio is. So if we dig into the force analysis more deeply with this set of meshed gears, then we can start to understand how this moving point of contact is going to influence the speed ratio. If we have just arbitrary variation of the contact point with respect to angular position, then there's really no guarantee we're going to have conjugate action. The speed ratio could vary quite a lot if we aren't explicitly designing a gear tooth shape that is going to assure conjugate action. And what would happen in this case? Well, remember the pitch circles? These are defined by the pitch radii, and these pitch radii up here, these relate to the speed ratio. If we have an arbitrary variation of the contact point in a way that it changes the speed ratio, it's going to effectively be shrinking and expanding the pitch circles. If we had a poorly designed gear animated like this, and at each time step we would adjust the pitch circles to show what the equivalent pitch radii and pitch circles are at each position, they would be shrinking or expanding, and it would be a lot more clear how the speed ratio is changing with this surface that does not provide conjugate action. If that's the case, the speed ratio changes with angular position. So this leads us to this question: can we design gears such that the contact point varies, but the pitch radii stay the same? The first part of this question, the contact point varying, this is something we're not going to get away from. If we have pairs of gear teeth coming in and leaving contact as the gears rotate, this gear set rotates, the point of contact is going to move. If we're essentially converting this rotational to translational motion, we're not going to have a feasible mechanical system where we can have a point of contact on a gear tooth that never moves and still have two circular gears rotating relative to each other. So we need to have a tooth shape such that we can take this contact point variation but control it in an ideal way such that somehow the pitch radii stay the same. And so is this something that's possible to do? The answer, of course, is yes, and the animation above here, this provides an example of that. And we're going to step through the force analysis that allows us to see why exactly this is true. There's something special that we notice about the forces as this point of contact moves across the surface of the tooth. The reaction forces, the contact forces, are always pointing in the same direction. And we're going to see why that specific property allows us to maintain a constant speed ratio. Gear geometry influences how the point of contact moves as the gears rotate. So we need to design the gear geometry such that we have the point of contact and the direction of the forces moving in a way that produces conjugate action. So we need to answer this question: what tooth shape will ensure a constant speed ratio? And this constant speed ratio, that's defined as conjugate action. We need to analyze the kinematics and forces of gear tooth contact and determine what shape or shapes can produce conjugate action. One way of conceptualizing this is to focus in on just a single pair of gear teeth. And instead of thinking about the whole gear with all the teeth, let's just focus in on these two teeth. We have one tooth here that's part of gear A, and then another tooth here that's part of gear B, and they're contacting at this point C. And as the angle, the angular position changes, the position of C along the gear tooth surface is going to change. So let's think of this in terms of just these two cams. These are in essence mechanical cams here, and we can have an input torque here applied to this cam. We're going to have some contact forces, some reaction forces here, and then we're going to have a reaction torque on the output cam or the output gear. We're going to assume here that there's no friction. So that means that there are no surface forces tangent to the surface at contact point C. If there's no friction, the only forces that are possible at the contact point are those that are perpendicular to the surface at the contact point. We're going to assume here that the cams roll relative to each other without slipping. And then we're going to ask, what forces are at play here, and what are their directions? What is the mechanical advantage between the cams? And then we're going to use force analysis to figure out the speed ratio. And just think back to the last lecture video. We went through in some depth in defining what is the speed ratio. We derived that both from a speed perspective and a force perspective. And we defined that with this rolling cylinder simplified model. But now we're going to get into the actual geometry of real gears and account for the complexities of pairs of teeth coming in and going out of contact at the mesh. Let's have a look at this rolling cylinder model again, where we have a driven gear down here. This is gear 2, and then we have a pinion or a drive gear up here. This is gear 1. They each have their respective pitch radius. We have an input torque, an input speed, output torque, and output speed. In this case, we're assuming opposite directions for the sign convention. And then the pitch point is the point at which the rolling cylinder model, the cylinders come into contact. And here we're wanting to figure out what are the forces that are present in an actual gear set at the point of contact between two gears. And again, we're going to focus on a single pair of contacting gear teeth and resolve the forces that are present for that gear. Here I've drawn the axis of rotation for both gear 1 and gear 2. I've also drawn the pitch point. I've drawn the pitch circles, or at least arcs of the pitch circles, and also the addendum and dedendum circles for each of these gears. Here is my attempt to draw two gear teeth that are just coming into contact. If this driving gear is rotating this direction, then this is the point at which they're just coming into contact. I've drawn the gear teeth to go all the way up to the addendum circle for the respective gears, and then the point at which they are beginning to contact, I've labeled that as point C. Here I've zoomed in on this pair of gears so that we can see more clearly the point of contact, and we're going to have a look at the forces that are present at this point of contact. Here we can see that the reaction force of each gear at the point of contact is perpendicular to the surface at the point of contact. Remember that we are assuming there's no sliding, there's no friction, and because of this there are no tangential forces. The only forces that exist are perpendicular to the tooth surface at point C. Based on these forces that I've drawn, our next step is to try and relate the torque values of the gears to these contact forces. To do that, we're going to need to identify what are the moment arms involved and go through and draw a more complete force diagram. Suppose here we're looking at the axes of rotation of both gear 1 and gear 2, and I've drawn the center line between these axes of rotation. Now I've drawn the point of contact C offset from the center line. I've also drawn the forces F1 and F2 and their directions that correspond to this gear position. We're going to define the pressure angle as the angle between the horizontal axis here and the direction that the forces at the point of contact are pointing. This pressure angle defines the direction of what we are calling the pressure line, or the line of action. And this line of action, where it goes through the center line, that is what we're going to define as the pitch point. As the gears rotate, the point of contact moves, the orientation of the tooth surfaces change, and therefore the direction of the reaction forces, the contact forces, could change as well. And if this changes, if the orientation of the surfaces change as the gears rotate, then the direction of the forces are going to change, and therefore the pressure angle is going to change. This is the general case with an arbitrary geometry for tooth shape. Now we're going to finish identifying the different forces involved here and see if we can back out some requirements that will allow us to have a constant speed ratio. One of the next steps here is to identify what are the moment arms associated with each of the forces at the contact point for each of the gears. If we draw a perpendicular line from the line of action to O1, this gives us the moment arm for F1, and that allows us to calculate the torque on gear 1, or T1. Similarly, we can draw a perpendicular line from the axis of rotation of gear 2 to the pressure line. This line is perpendicular to the pressure line, and that's going to be the moment arm for F2 that produces a torque for gear 2. And in this diagram, I've labeled L1 to be the moment arm length for gear 1, and L2 to be the moment arm length for gear 2. These are the torques for each of the gears that are due to the forces at the contact point relative to the moment arms L1 and L2. Here I'm defining R1 and R2 to be the pitch radii for each of the gears, or the distance from the axis of rotation to the pitch point. Let's zoom in on the geometry of this upper triangle that describes the moment arm and the pitch radius for gear 1. It's possible to show that the pressure angle, or that is the angle that the line of action makes with the horizontal in this case, or The horizontal line, more specifically, is a line that's perpendicular to the center line between the two gears. It's possible to show that if this is the pressure angle, then this angle over here is also the pressure angle. Similarly, let's focus in on the triangle that corresponds to the geometry of the moment arm and pitch radius for the lower gear. Based on these triangles, we can derive some relationships. Now that we know the length of the moment arm in terms of the pitch radius and the pressure angle for each of these gears, we can now quantify what are the torque values for each of these gears. We can say that the torque at gear 1 is equal to the force at the contact point F1 times the moment arm L1, or in other words, F1 R1 cosine phi. And then the torque at gear 2, that's going to be equal to F2 times L2, or F2 R2 cosine phi. Based on this, we can calculate what the speed ratio is. Recall that we can take the torque perspective or the force perspective to calculate what the speed ratio is. Plugging in the quantities from above, we can see that this is going to be equal to F2 R2 cosine phi over F1 R1 cosine phi. The cosine terms drop out, and we can also think about these reaction forces. If we had a case where the gears were accelerating, then we'd have a net force at the contact point because of acceleration. But here we're going to assume that we have quasi-static conditions, that we can neglect acceleration, and if that's the case, then we can claim that F1 is equal to F2, and then if that's the case, these cancel, and then we get the nice result that the speed ratio is R2 divided by R1. And then we can think back to how we defined the speed ratio before. Say omega 2, the speed of gear 2, that's going to be equal to omega 1 times the inverse of the speed ratio, R1 over R2. This may look pretty familiar, and it may be nothing surprising, but something important to pay attention to is we've derived this in a way that's quite general. R1 and R2, they could change as the gear set rotates and the contact point C moves. If the orientation of the teeth move, then the pressure angle is going to move. So suppose this contact point, what if we rotate some and the new contact point is right here, but what if the forces change and the new pressure angle is right here? Then that means the pitch point is right there, and R1 got smaller and R2 got larger, changing the speed ratio. In general, this is something that can happen. The speed ratio can change. So here we're trying to derive how do we get a tooth shape such that we keep a constant pressure angle, this line of action, so that the pitch point doesn't move around, so that the pitch radii R1 and R2 stay the same, so that then we get this constant speed ratio. Let's have another quick look at this potential for change of location of the pitch point and change of length of the pitch radii and the effect on the speed ratio. In general, the pitch radii can depend on phi, which is the direction of contact forces. Let's look at this in a little bit more detail. So here we have a representation of the forces and directions of two different positions of the same gear set, and this gear set does not have conjugate action. So in the position or the state depicted in the left-hand drawing, the contact point right here, it's on the left-hand side of the center line, we can see that the pressure angle in that case is quite a bit smaller than the pressure angle in the case on the right-hand side. And as a result, the pressure line could intersect the center line at a totally different location than it did previously. And this line or this point of intersection, this is called the pitch point. And the pitch point is what defines what R1 and R2 are. We showed earlier how we can relate R1 and R2 to L1 and L2, the lengths of the moment arms for the forces that are generated at the contact point. If a gear set had this behavior, if R1 and R2 change with position, then that means that we don't have conjugate action, that the derivative of the speed ratio with respect to angular position of the gear set is not equal to 0. And if that's the case, we're going to have a value for the speed ratio that varies with position, and this can cause all sorts of mechanical problems, including torque ripples, additional fatigue problems, vibration problems, and so on. We need to design a gear set that has a constant speed ratio. So now with all of this information that we've gathered, let's take a step back and reason through the requirements that are in place to make sure this happens. We want to have a constant speed ratio. That means the ratio between R1 and R2, the pitch radii, cannot change. And then equivalently, this means that the pitch point must stay put. For the pitch point to stay put, this means that the pressure angle, the angle of the line of action, cannot change. And then by definition, if this pressure angle is always pointing in the same direction, then that means that the forces at the point of contact must always be pointing in the same direction. Or in other words, at the contact point, the common normal must always point in the same direction. So what do I mean by that specifically? Suppose we have two curved surfaces coming into contact at a point. And at that point, they're going to have a common normal. And at least in the gear tooth contact case, the forces are going to be pointing in the direction of this common normal direction. And the key here is, as this contact point moves, as the gears rotate, we need the common normal to always be pointing in the same direction. So suppose we have the contact point move closer to the bottom land of the top gear and closer to the top land of the bottom gear. We need the common normal to still be pointing in the same direction with the same pressure angle. So how are we going to construct gear tooth geometry that achieves this? Let's move back to the slides and talk about this a little bit more. We're going to specify in more detail what do we mean by constant speed ratio requirements. If we want to ensure a constant speed ratio, how might this be achieved? We need to translate this requirement into actionable design guidance for gear geometry. Let's reason through this. We're going to present here a flow chart that shows how all of these requirements flow down into an actual guidance for geometry. We want a constant speed ratio, R2 over 1, R1, so that means R1, R2 are fixed and the pitch point is at a fixed location. At least that's one possible solution for satisfying this requirement. And the pitch and pitch radii, remember, these are defined by the intersection between the line of action and the center line. And the pressure line, that's defined by the direction of the forces, which is determined directly by the shape of the teeth at the point of contact. Because of that, equivalently, if the pitch point never changes, then that means we have an unchanging line of action direction. Or in other words, the pressure angle never changes. The derivative of the pressure angle with respect to angular position of the gear is 0. If this is the case, then the contact reaction forces are in the same direction. They're always pointing in the same direction. Even though contact point C moves as gears rotate, the forces are always pointing in the same direction. And we can achieve this by ensuring that the contact surface tangents are always perpendicular to the line of action at the contact point. So this is another way of describing in geometric terms the requirement of having a constant speed ratio. And so then the challenge becomes, how do we find a shape that achieves this? How can we keep reaction forces pointed in the same direction for any gear position theta? From the earlier animation, we can see when the contact point is close to the upper land of the right-hand gear, we can see what direction those are pointed. And then at a different angular position, the contact point is in a completely different position. It's close to the bottom land of the right-hand gear, and yet the contact forces are pointing in the same direction. We're going to go through one possible solution to ensure a constant pressure angle. We need two surfaces that are always perpendicular to the line of action at the contact point. Let's say these are the desired axes of rotation, and then these are the desired pitch radii. We want these to stay the same, and the pitch point to stay the same. Here are the pitch circles. Here is the desired line of action. We're going to assume it's some non-zero value. The next step in this construction is to draw some circles that are tangent to the line of action. These circles are smaller than the pitch circles, and we're going to define these circles to be called the base circles, and these are going to become important in constructing tooth geometry that provides conjugate action. Recall that when we were deriving the moment arm for the contact forces, we originally drew that moment arm out here, where it was basically a projection onto the line of action. But note that if we were to rotate the radius of this base circle, that it's the same length. So that the radius of this base circle is the moment arm. We need the contact force moment arms to always be the same length. And then these are going to provide a constant pitch radius as well. Here we are representing multiple contact points. Suppose we have a contact point right here and another contact point right here, and that at each of these contact points we identify what is the moment arm for the contact point forces acting about the center of each gear. We can draw another set of moment arms for a third contact point here. So we want these moment arms to always be the same, and if we have these moment arms always the same, then we're going to have the pitch radii remain the same, and then we're going to have the pitch point remain the same, and the speed ratios remain the same. Here's one way of constructing this. So looking at how we have these different contact points along this line of action, this suggests a particular way of constructing this geometry. Here is a base circle, and imagine that we have a string wrapped around this base circle, and we are pulling on the string, providing some tension, and as we unwrap the string from the base circle, we trace out a curve. And this is a special curve called an involute. And we can have a look at the properties of this involute to see whether it supports the requirements for a constant speed ratio. One main thing to observe here is if we use this geometric construction approach of unwrapping a string from the base circle, is that this line that connects these points at the end of the string to the base circle is always tangent to the base circle. Any point along this curve, if we were to draw a line that's perpendicular to the tangent surface, it would intersect the base circle in a way such that this line is tangent to the base circle. And because it's tangent, therefore, this is the moment arm for any forces that are directed in this orientation that is perpendicular to the contact surface. In other words, if we trace the path of an unwrapped string, it produces a tooth curve whose moment arm is always the base circle radius. And if it always has the same moment arm, then we're always going to have the same speed ratio. Now we're going to switch over to a demonstration of how this works. We're going to generate tooth shape by unwrapping a string from a base circle. For any rotational position, the common normal at the point of contact, or the line of action, the pressure line, passes through the pitch point. The point of contact is always on the line of action. The tangent plane at the point of contact is always perpendicular to the line of action. In a homework that in previous semesters was assigned to SE 410 students, there was some MATLAB code that was provided that, based on the concepts introduced here, generated the actual geometry for a gear tooth shape. And that's available to you on the course website if you're interested in seeing the code that can generate these involute shapes. Again, we're after this sort of behavior. When we have teeth come into contact, the direction that is perpendicular to the contact surface is the direction of the contact forces, and we want that direction to maintain the same orientation no matter what angular position the gear set is in. Let's zoom in on the geometry of a single gear. Here we have the base circle, we have the pitch circle. The pressure line is going to be tangent to the base circle, and it's going to go through the pitch point. Here is the pressure angle. For any angular gear position, if we trace an unwrapped string such that it passes through the pressure line, at that point the vector normal to the tooth surface will have the base circle radius as its moment arm. The moment arm does not change with position, and therefore the speed ratio does not change with position. In this diagram, we have the shape of an involute drawn in, and it starts off at the base circle here. And if you imagine unwrapping a string and drawing this curve, it's really only defined outside of the base circle. We can't define the involute on the inside of the base circle, and that's going to become important in the next lecture. Let's go through a physical demonstration to illustrate how we can generate involute tooth shapes. Here I am in my backyard. I've made a contraption out of styrofoam and wood and a little bit of cord, and I've created two base circles. So this is a smaller circle for the pinion gear, and then here is a larger circle for the driven gear. And you can see how I've attached the cord, and here I'm showing the center line between the axes of rotation for the two different gears. Putting these back on their shafts so they can rotate. Tightening up this string that connects the two gears, and this does a great job of helping us to visualize where the pressure line is between these two base gears. And then here is the pen that's representing a line that's perpendicular to the center line. Okay, let's actually start constructing tooth geometry. Just getting my pen set a little bit there, and I'm tracing out the shape of a gear tooth. And now I'm moving the gear, and I'm tightening the string back up. And so it's as if the tooth has moved to a different position. So we're looking at what the gear tooth would look like, what its curve would look like as we rotate the gear in different places. And now what I'm doing here is noting how at the point where these curves cross the pressure line, the surface is perpendicular to the pressure line. And it's hard to see from this view, but if you go through this construction yourself on a piece of paper, then it is pretty easy to see that these are in fact perpendicular. Now I'm drawing tooth surfaces coming from the pinion and showing how, as I trace the surface, if I rotate the gear to the right position, if I trace a surface such that the tooth surface is right up against the mating gear tooth surface, then they cross right at the pressure line, and at the contact point, the common normals point right along the pressure line. So now I'm drawing the pressure line. Now I'm drawing the center line, and that's the pitch point where the pressure line crosses the center line. Labeling that as the pitch point. And now if I draw this line that's perpendicular to the center line, I can identify what the angle is. Let's have a look at another concept now called contact ratio. And this is something that's important for designing practical gears. The contact ratio is the average number of teeth or pairs of teeth that are in contact at any one time. In this particular animation, it has a unique property where as soon as we lose contact toward the bottom right here, we gain contact at the top left. So it appears in this case the average number of pairs of teeth that are in contact is 1. And this is actually not a desirable scenario for a gear set. We'd like to have a contact ratio of greater than 1. It's going to provide smoother operation. If we have a contact ratio of less than 1, then that means we're actually going to have some positions where we totally lose contact, and that's a very undesirable situation. If we have a contact ratio greater than 1, it's going to be smoother and stronger, but to achieve these larger contact ratios, it may require larger gears, or it could require some other type of trade-off in gear design. Here we're going to go through and identify a number of quantities that are required to define what contact ratio is. We've already gone through many of these different terms, but there are a few new ones here. So here we are envisioning the pinion, or the driving gear, rotating counterclockwise, and then the gear, the driven gear, rotating clockwise. And so that means as teeth come into the mesh, the point of contact, the first point of contact is here at point A. We maintain this contact through the pitch point, and then we get to this contact point B, where we just lose contact. And then based on these 2 points, A and B, we can define a few things. For the gear down here, if we are starting at A, the angle of approach is this angle. That's the angle that the contact point sweeps through between A and the pitch point. And then the angle of recess is the angle that the contact point sweeps through between the pitch point and B. And we can define those similarly for the driver gear or the pinion up here. Let's zoom in on this geometry in a little bit more detail. And this is one of the places in class where you're going to have to draw from some previous knowledge in geometry. Identifying some of these quantities can be fairly non-trivial. Here we're going to identify the basics that you need to know, but actually calculating these quantities may require multiple steps. So here we've identified, well, what is point A, where we first come into contact, point B, that's where we lose contact. We have the angle of approach, the angle of recess, and then now we can define the arc of approach. This is along the pitch circle between point A and point P, and this is an arc rather than a straight line. And then we have the arc of recess between point P and point B. Notice that capital B is defined here to be a point on the pitch circle that corresponds to the angle of recess, whereas lowercase b, that's the actual contact point, and that's clear up at the top land there. The arc of action is defined as the sum of the arc of approach and the arc of recess. If we can determine the arc of action, this is one way of quantifying how much rotation can the gear move through while this one pair of teeth is still in contact. And then we can define the contact ratio to be the ratio of the arc of action to the pitch. And remember, this is the pitch that's measured as an arc length along the pitch circle. And so if we have an arc of action that is larger than the pitch, then we're going to have, on average, more than one pair of teeth in contact at a time. Let's talk about gear mesh requirements. If we have two gears that we want to mesh together, what needs to be true? They need to have identical pitch, identical pressure angle, and identical face width. What might happen if these requirements are violated? We will certainly have non-conjugate action. If they have a different pressure angle, we're not going to be able to assure a constant speed ratio. We may have geometric incompatibility. They may not even mesh together. If the pitches are different, the gears just may not fit together. Let's go through a systematic process for designing a full gear. And here we're going to be focused on geometry. There are other aspects of gear design that are not covered in this process. In this process, we're going to work through how do we define important geometric gear features. There are other considerations of gear design that we're not covering in this process right now, such as strength. That's covered in Chapter 14. Just a reminder what some of the key geometric features are of a gear. We need to specify, of course, the pitch. We need to specify what is the addendum, what is the dedendum. And all of these things need to be compatible, and we're going to do this in a way that provides a desired pressure angle and a desired speed ratio. Why is a design procedure needed? Sort of like with spring design, the design variables are interrelated, and arbitrary combinations of design variable values may not be compatible, or they might not correspond to a design that's physically meaningful. And so rather than using a trial and error process and intuition to arrive at a set of variables that is a valid design, here we're going to use a systematic procedure that reduces the difficulty of the design process and can help improve design outcomes. In addition, we're going to aim here to gain design insights from these quantitative relationships present in this systematic process. And these relationships are going to connect design elements, such as design decisions, and spur gear properties that we need to make sure are satisfactory. This is a 5-step procedure-based design process that is outlined in the textbook. First, choose the speed ratio based on system design requirements. If you're using a gear set in some system, you may have a very specific speed ratio that you would like to achieve, and that's a good starting point. Number 2, choose integer values for N1 and N2, or the number of teeth on gear 1 and the number of teeth on gear 2. One important thing to consider here is that in a real gear, these must be integer values. And so this ratio, N2 divided by N1, may not necessarily always give you exactly the speed ratio that you want. This is going to restrict the speed ratios that are possible to realize. We're going to have possibly some error between the desired speed ratio and a realizable speed ratio. So we can ask this question: if we want to have a more accurate speed ratio, would we need to increase or decrease overall gear size? Would we need to have larger or smaller pitch diameters? After we go through some more examples using this process, this should become more clear. To increase the precision of the speed ratio, we need to have more teeth. That's going to allow us to more easily achieve a target speed ratio. Because of strength and kinematic requirements, there is a limit on the number of teeth that we can have on any given gear. If we need to increase the number of teeth on a gear, it turns out that we may need to increase the diameter or the overall gear size. Step 3 in this process is to choose the diametral pitch, which is essentially the inverse of the pitch. And this is going then to dictate the diameters of the gears. If we have chosen what's the speed ratio, what are the number of teeth for each gear, and then we specify the diametral pitch, this allows us to specify exactly what the pitch diameters are. So pitch diameter is equal to the number of teeth divided by the diametral pitch. And remember, meshing gears must have the same pitch. And remember, if we want to relate this back to circular pitch, it's just pi divided by the diametral pitch. There are geometric limits on pitch diameters due to things such as interference and constraints on contact ratio. We're going to discuss these limitations a little bit later. Another consideration is gear strength. For example, we can look at tooth stress from bending and also fatigue considerations. These are treated in depth in Chapter 14. There is also a public lecture video that you can go through that covers a large portion of Chapter 14. There is typically a trade-off between strength and size, mass, cost, and packaging in making decisions about gear design. We can make a gear stronger pretty easily by making it larger, but then that's going to cost more. And in some systems, it's important to have a really compact gear set. It could cause some issues with packaging. In this case here, we're going to focus just on geometry and kinematics. We're not going to be looking at strength, and we're also not going to be looking yet at interference considerations. If we consider increasing or decreasing gear size, and we have a given amount of torque that we need to transmit with a gear, what would happen to the actual tooth contact force if we increase pitch diameter? If we increase diameter, or here in this equation increase R, but the torque is held fixed, it's going to reduce the contact force. And for a given level of torque, we're going to have this lower force, and then that's going to increase the safety factor for the gear. So not just because we have a larger, stronger gear will a larger gear set be stronger, but because we're actually reducing the contact forces. This is a strategy that we talked about previously in class in the section on shaft design, where this was a possible strategy for reducing the radial loads on shafts. So it's not just the gear that we need to worry about. We need to think about what is supporting the gear, and if the shaft supporting the gear is deflecting too much because of a large radial force, or that large radial force is causing too much bending stress in the shaft, then it may be advantageous to see what we can do to reduce the contact force. Larger gears, in summary, are stronger for two reasons. Larger, stronger teeth are possible, and number two, we have lower contact forces. But the drawbacks of larger gears include having more mass, a larger mass moment of inertia, so that's not good for dynamics, and they're more expensive, they take up more space. So these are nice examples of design trade-offs that need to be considered when making design decisions about gear sets. Let's keep going with this 5-step procedure-based design process. Step 4 is to choose the pressure angle. The range of 20 to 25 degrees is quite typical. Almost always right now it's 20 degrees in commercially available gears. In the past, 14.5 degrees was used. The pressure angle defines the base circle radius and the moment arm length. So the base circle radius is going to be equal to the pitch radius times the cosine of phi. The next part of step 4 is to define involute tooth shapes. At this point we know the pitch radii, and we know the pressure angle. And those are the quantities that we need to know to define the involute tooth shapes. One way of defining it or expressing it is using this template. There are also software tools that can help in generating involute tooth shapes. For example, the MATLAB code that I mentioned earlier regarding a previously assigned homework problem, and then also commercially available tools such as Autodesk Inventor have involute shape generators. The final step is to define the addendum, dedendum, and tooth thickness. This is perhaps the most straightforward step. The addendum is defined as 1 over the diametral pitch. The dedendum is 1.25 over the diametral pitch. So why is the dedendum larger than the addendum? Why are we using 1.25? This allows clearance. So this difference between the clearance circle and the dedendum circle is made possible by using 1.25 instead of just 1 divided by p. If we used just 1 over p, then the top land of the meshing gear would be right up against the bottom land of the lower gear here. Tooth thickness is pitch divided by 2. This helps make sure we don't have any backlash. There are some issues if we have imperfect manufacturing. We could end up with some backlash or difficulty in meshing if the size is too large. We should think beyond the 5-step design procedure. We need to think about things such as contact ratio. We want to make sure it's greater than 1, certainly, usually greater than 1.2. We need to think about gear strength and fatigue, and a number of design elements that come into play here include the tooth face width, tooth thickness, bending stress, contact forces, and other factors. These are covered in Chapter 14 and also in the corresponding YouTube video. We need to consider what's called interference. We're going to cover this in some more detail in the next lecture. This addresses a possible situation where the contact point between two gear teeth could be where the shape is not an involute. And remember, the involute shape is only definable outside of the base circle. Anything that is smaller in diameter than the base circle is a non-involute shape. This interference consideration places minimum limits on the number of teeth and pitch diameters in gear design. Violation of these limits can produce problems with both kinematics and wear. We're going to go through another gear geometry design example to wrap up this lecture. We're going to base this example on the physical demonstration that we saw a few minutes ago. And in going through this design activity, my objective was not necessarily to maximize or come up with some ideal mechanical properties, but I was more interested in creating something that was good as a visualization. I wanted to illustrate how we actually generate these involute shapes and do it at a scale that would be easy to film and to demonstrate. One observation I made was that it might be really nice if there's a big gap between the base circles, so it's good for visualization. If we only had a tiny gap between base circles, imagine, for example, a gear set that had some really tiny teeth on them, it would be really hard to follow how we are tracing out these involute shapes. And so I wanted to have a large gap between base circles. So this is the gap between base circles in this figure, and we can calculate that gap as the sum of the pitch radii minus the sum of the base circle radii. Here we can see what that gap looks like in this zoomed in figure. So here's a base circle, and then here's the other base circle. And so the gap between those base circles are what we're trying to make sure is sufficiently large. So we want this quantity to be large, and if we want that to be large, we need the difference between the pitch and base circles to be large. So now if we go back and think about the relationships between these quantities, the base circle radius is equal to the pitch radius times the cosine of the pressure angle. This tells us something about the pressure angle. If I were to choose phi equals 20 degrees, maybe that is going to give me some reasonable gap between the base circles. But what if I chose something different? If we choose large pressure angles, then that's going to increase the difference, the relative difference between the base circle and the pitch circle size. And in the extreme limit, if the pressure angle approaches 90 degrees, then the base circle approaches 0. And of course, that's not physically meaningful. So we need something that's less than 90 degrees, but maybe larger than 20 degrees. We'd also like to have large pitch or tooth thickness. This is also going to help enhance visualization. There are, of course, some potential problems using this approach. If we were designing an actual gear, this might produce a low contact ratio. It could result in non-involute contact or interference, and it might also result in stress or fatigue problems. But in this example, we're focusing on geometry only, and in later lectures, we'll consider some of these other issues. Let's go through the 5-step design procedure for this particular problem with this physical demonstration example. Choose the speed ratio. Here I chose 1.5 as the speed ratio. That way there is some difference in size between the pinion and the gear, but not an exceptionally large difference. Step 2, choose integer values for n1 and n2. If we choose values that are too high, the teeth are going to be difficult to visualize. So we want lower values for n1 and n2, but that can bring its own challenges as well. The strategy that I chose to use here is to start off choosing n1 and then just multiply that by the speed ratio. I have to be careful here, though, because multiplying something by 1.5 will not necessarily always give me an integer for n2. So I have to be careful in what I choose for n1. Here I chose n1 equals 12 teeth, and then that gives us 18 teeth for n2. Step 3, choose the diametral pitch. The tooth size needs to be large to aid visualization, so this means we need a smaller diametral pitch or a large circular pitch. Here I chose the diametral pitch to be pi over 2 teeth per inch, and then that produces this convenient value for circular pitch of 2 inches. In going through this procedure, I did need to iterate some. I actually coded the formulas required for this in MATLAB to speed things up, and I adjusted some of these design variables until I arrived at a consistent set of quantities that was going to work for this visualization example. Step 4, choose a pressure angle. I mentioned before that I'd like to choose something larger than 20 degrees, but definitely less than 90 degrees. Here I chose 30 degrees. This large value increases the gap between base circles, but of course, I need to point out this caveat: this could cause mechanical problems. It is good for visualization, but this is not necessarily something that you should do in an actual mechanical gear design. Next step, calculate geometry for physical demonstration. These are some of the quantities that I needed to actually cut out the base circles and determine how to assemble everything together. So the pitch diameters are 7.639 and 11.46. So these are a reasonable size to manage physically. The base circles are smaller than the pitch circles. The base circle gap turns out to be 1.279 inches, which I hope is reasonable enough to provide a good visualization. After that, we need to define the involute shapes, and in the previous video, there's the demonstration you can see of how we can, at least very roughly, very approximately, generate the involute shapes by actually unwrapping a string from the base circle. Of course, we would need to do this in a much more precise way if we're going to actually design a gear for production. The final step is to define the addendum, dedendum, and tooth thickness. So remember, the addendum, that's the distance above the pitch circle; dedendum, the distance below the pitch circle; and the tooth thickness here, that's the arc right at the pitch circle. So the addendum is 0.637, the dedendum is 0.796 inches, and the tooth thickness is 1 inch. Remember, previously we saw the pitch was 2 inches, and this was convenient because of the way I defined the diametral pitch. With that, we're going to end this lecture. I hope this introduction to conjugate action was helpful as we go through the process of learning to analyze and design gears.